Okay, let's get started. So last time we discussed equivalence and similarity of matrices. Are there any doubts from that session?
Sir,
Sorry.
Yeah.
so like when we have that like formula for similarity, right? B equal to P inverse AP.
Yes.
So basically, in that formula, say for example, for P as well as A, the matrices.
Mm-hmm.
So like the basically the transformation matrix, the matrix that we get for P as well as A, they are in the same basis, right?
Well, P is not the matrix of any transformation. So when you're talking about the matrix of a transformation, we talk about whether it is in this basis or that basis. P is
Yes,
just a matrix.
correct. It's a matrix that we find out from the basis, right?
Yes, using the basis that are specified. Yes.
Okay. And okay, got it.
So when you say matrix, it is just an ordered arrangement of finite arrangement of elements in real numbers or whatever field you're working with. So that does not have any appeal to any basis. But the way you find it is using the given basis. Yes.
Mm-hmm. Okay.
So equivalence was B is equal to QAP, and similarity was is B is equal to P inverse AP. Now here this could be rectangular matrices as well, the general class of matrices. Here we do require that all the matrices involved are square matrices. And then in the case of equivalence, we did see that equivalence is related to the rank being equal or transforming one matrix from transforming one matrix to the other using just row operations, column operations. And similarity was, and of course, equivalence is also linked with representing the same transformation using different bases. So there you are allowed different bases on the domain and codomain. But in similarity, you take it a little bit more sharp and you only allow that you only allow transformations from a space to itself and the same basis on both sides. And that is these are all the notions that we saw last time.
Same basis on both sides means for B also we'll
Same
have to,
basis. No. So for B
right.
and A represent transformations using different bases,
Correct.
but they are the same on the both sides. So it is the same. You're taking TBB, you take beta beta, you get A, and you take gamma gamma, you get B. So you're using different bases, but while you're considering one of them, you're using that same thing on both sides of
Ha.
the transformation.
Okay. 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 If you are using beta,
So
we'll
it's
use
like
beta only, and if you are using
yeah.
gamma, we'll use gamma only, right?
So these are the two matrices that you're actually relating. Matrix of the transformation with respect to beta on domain and beta on codomain, and matrix of the transformation with respect to gamma on domain and gamma on codomain. So these are similar matrices is what we saw at the end of the session last time.
Understood. So basically, if you are using beta, then we'll use beta only. Else, and if you are using gamma, then we'll
Yeah,
use gamma only.
yeah, gamma on domain and codomain.
Gamma in
So
combination.
you'll get different matrices, right? In that case, by using beta beta or gamma gamma, those matrices are similar. This is what we had seen. And yeah, similarity. One of the properties that we saw was similarity implies same determinant, rank, and trace. Trace being the sum of the diagonal elements. But even if two matrices have the same determinant, rank, and trace, that does not imply that it is similar. So to prove that they are similar is more difficult. This is as opposed to equivalence, where equivalence is if and only if same rank. So Equivalence is also easier to verify in a sense that I can just check the rank, and if they are same, they're equivalent. But for similarity,
So
at least
basic,
there is no
so
sure shot
basically for
approach to,
basically for similarity, if two matrices are given, then
yeah.
once we either have to do if the full and final proof is basically B equal to P inverse AP, right? That is
Yes, that's what it seems like now, but then as in you are not in this course at least you're not going to see any other method, but using eigenvalues and all those things, there are ways.
okay.
But yeah, it's not covered in this course. For this course, and you will not also be asked
Sir, can we
questions which
use
are,
the eigenvalue method? Like, is it reliable?
yes, there is a method which gives you, I don't remember the exact conditions right now, I don't
Okay,
recollect it,
okay, okay.
but there is a method to do it because finding if there is a possible P such that B is equal to P inverse AP is very difficult. So even in a 2 cross 2 case, you will have four variables and you'll have to solve an ugly system. So that is not the only way. There is a shorter way, but that is not covered in this course. So here you will mostly just see if it is similar, then find something. So you'll probably be given two matrices, and if they are similar, then you have to say uh, what. So there'll be maybe one unknown quantity. Using determinant, rank, or trace, you'll have to determine what that unknown quantity is. I think we saw questions of that form last time. Now let us move on to affine transformations and affine subspaces. Now this affine subspaces and transformations does seem a little uh, isolated in that it is not exactly related to the concepts that we have been discussing. So it's like we have had a map, right? We have vector spaces, then we saw basis, which is a easy way of representing vectors in a vector space using just finitely many elements. And then we saw linear dependence and independence, which led to the basis actually. And then we saw transformations, which are maps between vector spaces. And then we saw transformations using basis can be represented as matrices, and we have been trying to weave the story. And this affine subspaces and affine transformations is a bit of a sideline, and it's kind of a minor topic. We'll just cover the definitions quickly and then go back to this vector spaces thing. So, but nonetheless, it is natural. So to motivate this, what are the vector spaces or vector subspaces of R3? Let's say R3. Can you give me the entire list of vector spaces of R3?
So line, plane, as well as the whole space.
Yeah, so first of all, you have the trivial ones,
Trivial
which
matrix.
is this and this. These are the trivial vector subspaces. And then you have lines,
R2
but there is a condition, right? There is lines through the origin
origin, through the origin.
and planes through the origin.
Point.
Point is not a subspace unless it is the zero vector, which is this. So an arbitrary point is not a vector subspace.
Okay.
But it is a good point to bring up because that is what we'll be seeing next. So even though these are all the vector subspaces of R3, and we worry about or we say that a linear structure is easy to work with. That is sort of the philosophy. A, a line like this also has a linear structure in the sense that the data or the points on the line are arranged in a linear fashion. So the bigger subset or the bigger set which accommodates such examples also, like lines not necessarily passing through the origin or planes not necessarily passing through the origin, is that of affine subspaces. So let us say this point, this line is given by y is equal to x plus 1. This is a slope 1 line with the equation y is equal to x plus 1. So how do you represent this as a set? Let's say I want to write this as set. So can you give me the set theoretic representation of this line? What does a point
All
typically
like
look like?
um,
Yeah, go ahead, please.
Sir,
So of
x
course you
comma
can,
y where y equal to x plus 1.
yeah, this is one way to write it, but this is not what I want. I want to see it as a one parameter family, highlighting the fact that this is in some way one dimensional. So I
X
want to
comma mx,
express it.
x comma mx plus 1 something.
Yeah, okay, fine. Let's take that itself, x itself. This I can write as x comma x plus 1, right? So this is here, it's not mx, but it is just x because I've
Yeah,
just taken y is equal to x plus 1.
yeah.
So it's x comma x plus 1. So this highlights the fact that this is a one-dimensional space. So like one parameter is enough to describe the set. So this I can write it as, so without going into the formal framework of what it means to say a set plus another point, that actually doesn't make sense, right? What is a set plus point? What I mean is I just take elements from the set and add it to the point. So if I take any point of the form x comma x and add the fixed vector 0 comma 1, I get the whole space back, right? I can write it this way also. And what is this?
It's a subspace, sir, uh,
Yeah.
of R,
So let me call
R to
this
Y.
where U is span of 1, 1 is a vector subspace. So from lines through the origin, I want to try and capture every possible line. Let us say that is my objective. So can you see that every line can be written as every line can be written as, let's say in R2 itself, for the time being, where U is a vector subspace of dimension 1. Do you see this? Instead of taking y is equal to x plus 1, I can take y is equal to mx plus c. Right? That's the general line. I want to form a class of subsets which captures all y is equal to mx plus c. And that can be written as x comma mx. Of course, there's this one more line, x is equal to 0, but let us just forget that for now. Sorry. Y is equal to mx plus c. So this will be x comma mx plus c. This I can write it as span of 1 comma m plus 0 comma c. Do you see what's happening over here from here to here?
sir, how 0 to C? Here put the value of x is 0 like this.
So x comma mx plus c,
Yeah.
any point over here in this set is of the form x comma mx plus c. I can write this as x comma mx plus 0 comma c. This is just definition of vector addition, pointwise vector addition. Now this
Okay.
is x times 1 comma m plus 0 comma c. right? So x times 1, and the variable is x over here. So as I vary x, I will get the entire span of 1 comma m, and I'm adding this fixed vector 0 comma c to each of those guys. So that is what this means. Span of 1 comma m plus 0 comma c means I'm taking vectors in the span of 1 comma m and adding the fixed vector 0 comma c. And what the set of all points that I obtain is the line y is equal to mx plus c. Is that clear?
Excuse me, sir.
Yes, sir.
What is the terminology word of span, sir? Because
Span is the linear span. So we are in Rn. So this is just all possible linear combinations using vectors from the given set. In this case, the set that is under consideration is a one element set 1 comma m. So linear combinations of 1 comma m is just multiples of 1 comma m. All right. So is this okay? This equation?
Yes, sir.
Okay. Now, in general, what we have is a set which can be written as v plus u. So v is a vector in a vector space, and u is a subspace of the vector space, is called an affine subspace. Once again, what is this set v plus u? What do I mean by adding a vector and a set? That is, I take all possible vectors from u, add this fixed vector v to them, and the set of all vectors that I obtain this way is called is denoted v plus u, and this is the definition of an affine subspace. So these are just translates of linear subspaces. So if I take a linear subspace and translate, so I used 0 comma c, right? So if I use 0 comma 1 over here, or in general if I use just 0 comma c, I'll see that this line. So what happens if I take this line y is equal to x and take every point like and shift it by 0 comma 1, or translate it, add 0 comma 1 to it? What I get is y is equal to x plus 1. So taking a vector subspace and adding a fixed vector gives you some sort of a linear structure, but as if the vector that you're adding is not 0, then it will not pass through the origin. So it will not contain the 0 vector. So this is the bigger class of subsets of a vector space which are interesting, called the affine subspaces. So every affine subspace can be written as a vector plus a usual linear vector subspace.
Sir, a point. I'm having a doubt out here. Sir,
Yeah.
you meant usual subspace means the subspace which has a zero vector in it. Can we
Yes.
define like that?
Yes. Yes. Usual subspace is that vector subspace.
Like, can we also define it like trivial subspaces of the R cube, or like,
Not necessarily trivial subspaces, right? You can say lines through the origin are not trivial subspaces,
oh
because
yeah,
trivial
yeah.
subspaces uh, generally used for the zero subspace and the whole space. So you can take lines and translate them, planes and translate them. Take, for example, x is equal to 1. This, let me just put it over here. Example, in R3, you have x, y, z, x is equal to 1. Is this a linear subspace or is this a vector subspace?
Yes, sir.
The
No,
points of
why is
this
not there then?
are of the form 1, y, z, no?
Zero has to be there. Zero, zero, zero.
It's not.
So this is not a vector subspace. So this is not a vector subspace. Simply because 0, 0, 0 is not there, as many of them have pointed out. But this is still a plane which does not pass through the origin. So every point is of this form. And these points, I can write it as 1, 0, 0 plus 0, yz. Now, what is 0, yz? 0, yz is the plane which is given by, just to rewrite it in a more familiar fashion, x is equal to 0 or the yz plane. So the yz plane is a vector subspace, and you're adding this fixed vector 1, 0, 0 to it to get the plane x is equal to 1. So this is an affine subspace. So to summarize, affine subspace, the definition is you take a fixed vector in the vector space. Note that this need not be in U. This is in V in general. Of course, if it is in U, then you will get the original subspace only. Well, not really, but okay. Uh,
Sir,
yeah,
affine subspace.
yes.
I really don't get that.
That is the definition that I'm giving you, that you take a vector subspace and then add a fixed vector. You take all possible vectors in U and take a fixed vector V and add V to all possible vectors from U. The set that you obtain, this is called an affine subspace. And to visualize it, you look at this line y is equal to x plus 1 or the plane x is equal to 1. So let's focus on y is equal to x plus 1. Y is equal to x plus 1 is not a vector subspace because 0, 0, it does not pass through the origin. 0, 0 is not a part of that set. But it can be written as 0, 1 plus y is equal to x, or this u I can write as y is equal to x, or x comma x, the span of x comma x, or the span of 1 comma 1, whichever way you want to see it. You can take this line with slope 1 which passes through the origin and shift every element using the vector 0 comma 1. You can add 0 comma 1 to each vector of the line passing through the origin, and the line that you get, the set that you get, is actually a line which does not pass through the origin. And this is the prototype example for an affine subspace where you take an element from a given, where you take elements from a given vector subspace and add a fixed vector to it, translate it by that vector, and the resulting thing is what we call an affine subspace.
Sir, I think, I mean, even I am having that problem of understanding. Okay, you get this definition, but they've done this whole work of defining vector subspaces. Why not straight away
Yes.
talk about affine subspaces and it covers both? Because
That's a good question. So the affine subspaces do not enjoy many of the properties that vector subspaces do. Like, these are not very easy to see. These are relevant in certain contexts. The most applicable notion is that of a vector subspace. And we have seen whatever. So this is a bigger class, right? So the smaller class of vector subspaces enjoys more properties. So that is why we have seen that and the properties that it enjoys. Because if you straight away start with an affine subspace, then you'll have to just restrict to vector subspaces. It's just a stylistic choice. You could learn it that way also. And affine subspace for which v is equal to 0, that is a vector subspace. You can start out with an affine subspace and then come down to vector subspaces that way as well. That is also valid, but this is just since this is there just for completion, this is just introduced much later.
Sir, just one question. Can we say we write a affine subspace with respect to origin? We try to writing in.
Are you saying just do 0 plus u?
Yeah, like in a equation, y equal to mx x plus 1. After that,
Yeah.
we draw a similar line that passes from origin and we comparing from
Yes.
here. That, so just I want to conclude it. We affine subspaces we write in a with respect to origin, like, or we
In a
compare.
affine subspace, we write in reference to a vector subspace. We take a vector subspace
Okay.
and we add a fixed vector to all elements of that, and what you get is an affine subspace.
Okay, sir.
Okay, just as we did over here or over here. So over here, what is
Sir,
the associated vector subspace? That is x is equal to 0. For the affine subspace, x is equal to 1. The u is x is equal to 0. And then the v is 1, 0, 0. So this set plus this element for everything gives you this set.
Yes, sir.
Okay. Yeah. Any other doubts?
sir, 0 plus u is, can we say, is it an affine subspace?
Yes. But what is 0 plus u?
Like, adding 0 point.
Yeah. But addition of 0 gives you what? These are all the elements. 0 plus u, u in u. But what is 0 plus u? It is an additive identity, right? 0 is an additive identity. So what would 0 plus u be?
U.
Yeah. So this is just u where u is in u, which is just u. So what you have concluded is every vector subspace is an affine subspace.
But is the vice versa true, sir?
No, it's not, right?
Okay.
So take y is equal to x plus 1. It does
Understood.
not pass through the. So lines in general, for example, are vectors, are affine subspaces. But lines through the origin are vector subspaces. So every line through the origin is a line, but every line is not a line through the origin.
So basically,
It's
like, it becomes like a parallel space sort of a thing, right?
exactly. It's like a
With some
parallel version. So
translation
even
as
in,
well.
in in the case of planes also, it's the same thing. So you take a plane through the origin, and then you look at all parallel planes.
Correct,
Those
correct.
will be affine subspaces.
Yes, and if
So
they are
this,
not
of
passing through
course,
the origin, then they'll specifically be affine subspaces only.
yeah, there will be affine subspaces which are not vector spaces, if that
Not
is
the
what you mean.
yes, yes.
Yeah.
So one more example for a fine.
You can just take any vector subspace. Now that you know, okay, we'll take one more example, which is more interesting. Uh, Before that, I'll just say that let us use L for a affine subspace. If What do I mean by an affine subspace? You can write this as V plus U. So can I write it as V plus U uniquely? This is a question. And U is unique. V is not. Now, what do I even mean? Let us take the same example, y is equal to x plus 1, and I'll demonstrate over there why u is unique. I won't give you the proof of why u is unique, but I'll say that v is not unique. That I'll demonstrate using an example. Now, we considered the line y is equal to x, and this line y is equal to x plus 1. Right? So this is y is equal to x, and this is y is equal to x plus 1. So if I take a point of the form xx and then add this vector 0 comma 1. What is the vector 0 comma 1? That is just this vector, right? Let us take it straight. Assume that it is straight. No, this should be good. Yeah. So this is the vector 0 comma 1. So if I add 0, 1 to this vector, what I get is this red line. If I add the red vector to the points on the black line, I get the red line. But I could have, if I take all elements of the form x comma x, and then let's say I'll add 1 comma 2. What are all possible vectors I'll get if I consider this set? This can be written as x plus 1, x plus 2, where x varies in R. But this is also the line y is equal to x plus 1, because here you see that this y is equal to x plus 1. No, it's like x plus 2 is equal to x plus 1 plus 1. And as you vary x, you will get the same set. So instead of translating like this, what I've done is I've translated using things like this. So I can translate using these also.
Sir, why we have added x plus 1 and x plus 2?
We are varying x. I'm just saying that instead of adding 0, 1 as the fixed vector, I'm using this vector 1, 2. And the set that I get is the same. So suppose u is equal to xx as x varies in R. Then what I'm saying is 0, 1 plus u is the same as 1, 2 plus u. Why is that? Any element of the form 0, 1 plus u is like something like x, x plus 1. That I can write as, this is the same as x minus 1, x plus 1, 2. So let me call this set L1 and this is L2. I'm trying to prove that L1 is equal to L2. I take an arbitrary element in L1, which is of the form x, x plus 1, and I write it as x minus 1, x plus 1, 2 will not work. Wait. This is x minus 1, x minus 1 plus 1, 2. But this is an element of u. U was y is equal x, x. So this is an element from that set. So this actually belongs to L2. Every element of L1 is in L2 and every element of L2 is in L1. This is a formal way of proving it. But the upshot is that you can express an affine subspace using different representatives for the vector that you're adding. So this V is not unique. So you can have a given affine subspace which is expressed as V1 plus U or V2 plus U. The precise set of all vectors that give the same affine subspace is actually the vectors of L. So for any V in L, L is equal to V plus U. You can write it this way. Until which point will you guys follow me? Are you all with me through to the end?
Yes,
Can you
but is
explain,
there a
sir?
way where we can determine that which which family of these vectors will satisfy that? Like in case like you are given are these two equivalent? Like for like a one-dimensional thing, it looks easy to do.
Yeah.
Is like the same thing if it is carried to higher dimensions, uh, and some I'm just saying that like you might get a question, are these two the same or something? Is it easy to prove that like by just like you did here, x minus 1 x minus 1 sort of thing, and we can work that out that these two are actually same?
So the underlying vector subspace has to be the same. This there is no choice. I'm
Yeah.
not going to prove this statement. And then what are all the v's that are permitted to be added to the given u is any vector of L itself. So suppose you are given uh, x is equal to 1, the other example that we are showing. So I can say the corresponding subspace is x is equal to 0, right?
Mhm.
plus what are all the vectors that I can add. I can add any 1 comma y naught z naught, and I will get the same thing. So why? Because 1 comma y naught z naught is an element over here. So for the given affine subspace, you can pick any vector from the given affine subspace, and that can be the fixed vector that needs to be added to the corresponding subspace.
Okay.
So in this case, you see 1 comma 2 was also in that line, in the line y is equal to x plus 1. I can, as soon as I say, suppose, is this true? This is not true because 1 comma 3 is not on the line. So any vector on the line itself can be added. In general, any vector on the affine subspace can be added to the corresponding vector subspace to get the affine subspace itself.
Sir,
So can
both of them
Yeah.
are affine subspace now. The parallel lines are not affine subspaces of each other.
Parallel, there's no affine subspaces of each other. Affine subspace is a independent notion. So all lines are affine subspaces.
So, in one sentence, if we say affine subspaces,
Affine subspaces are all possible. I mean, the trivial affine subspaces are points. You have points, lines, planes, and higher dimensional hyperplanes in higher dimensions. Whatever you have the notion for vector spaces, you translate it, you get the notion for affine subspace, which means adding a vector, adding a fixed vector. And what are all the possible vectors that you are allowed to add is actually any vector of the given affine subspace. Alright.
can we say that the different vectors that we are adding, they will always have a constant difference between them, like 0 1 1 2, like that? I mean, can
No,
we?
the difference that they have will actually be an element of your underlying subspace, corresponding subspace.
Oh,
So, if you can write the same element as say v1 plus some u1 and v2 plus some u2, your v1 minus v2 has to be equal to u2 minus u1, and this is in u. So the difference between any two elements that are permitted for the representation of the affine subspaces has to be in the corresponding vector subspace.
okay.
All right. And do not worry too much about this. This is covered very quickly, and the questions are also just find the corresponding subspace. So example, if I have x, y plus 3, and let's say x plus y plus 2, x, y, z. No z, right? That's what. Now, what is the subspace corresponding to this affine subspace? First of all, is this a vector subspace?
No.
No.
Well, let me just do this. No, then it would be. Yeah, let's not do that. Yeah. Why is this not a vector subspace?
0 0 0 is missing.
So, have you verified that 0 0 0 is not a part of this?
To make so if y is minus 3,
Y is minus 3.
then
You'll need y is minus 3 and x is equal to 0, but then this will not be 0. So,
yeah.
yeah,
Yes.
0 is not there, so this is not a vector subspace. So this, but is this an affine subspace? So take, you can clearly see that over here it is x, y, x plus y, the set of all elements of this sort. And what is the vector that you need to add?
0 3 and 2.
0, 3, 2. So this is the vector subspace which corresponds to the given affine subspace. First of all, this set can be written as a vector plus a vector subspace. This is a vector subspace, right? This is just z is equal to x plus y. The plane given by z is equal to x plus y. Or you can verify using the axioms of a vector subspace that this is actually a vector subspace. And this is the u. And this is one possible v. You can have other v's as well. But more often than not, what you're worried about is what is the underlying vector subspace corresponding to the given affine subspace. And in this case, it is x, y, x plus y, or z is equal to x plus y, whichever way you want to represent. All right, let me move ahead with affine transformations. Affine transformations is even more abstract and difficult to understand. This, you just make note of this definition, and even questions from here, well, most of the time there won't be questions. It will just test the knowledge of the definition, even if it is there. So what would an affine transformation be? It should be a map from an affine subspace L to another affine subspace. Let me call it L1, L2. Now, but what is L1? It's an affine subspace. So there is a V and there is a U1. And this one can be written as f of V plus U2, because f is a map from L1 to L2. So f of V is an element of L2. And as long as it's an element of L2, I can use that to represent the, to give it this vector plus vector subspace transformation. So the underlying subspaces of L1 and L2 are U1 and U2 respectively. And I'm just choosing to write it this way. Now this is said to be an affine transformation if T from U1 to U2 given by T of U is equal to. So I'm defining T as this, f of U plus V minus f of V. First of all, f need not have the linear transformation property. So this is not automatically equal to f of U. If it was a linear transformation, you know that f of U plus V would be f of U plus f of V. So then f of V would get cancelled and you would get f of U. But in this case, this is a transformation between affine vector spaces. So it need not have that property. And if the map that we define this way is a linear transformation, you know what a linear transformation is. You can check if something is a linear transformation, right?
Yes, sir.
Then that f is called a affine transformation. So just make note of this definition. What does this actually mean? You can go back and see the prof's video, or at the end, if there is time, I'll come back. What is important is just knowing the definition, which is there mostly just for completeness.
So it looks like it's saying that the transformation is not applied on the vector itself. We are
Could you repeat that? I didn't understand.
undoing the effect of it. Is that what it's saying? Like,
in some sense. So what's happening is, this might make you a little more confused than you already are. So you will have two transformations, right? So these are like two affine subspaces, lines not through the origin. So in some sense, you go back to the origin, as in you look at the corresponding vectors in the vector spaces which correspond to these affine subspaces, and there it has to be a linear transformation. It is something like that. Do you
Okay.
get what I'm saying?
Yeah. I think I get it. Yeah.
Yeah, and this actually can be made more robust. But yeah, I'll have to go into a lot of details. What this essentially does is that these affine transformations can be taken back by subtracting v from every vector. I can take it back to uh, the corresponding subspace, right, u1, and then I can look at its image and take it back to u2, and that thing has to be a linear transformation.
Sir, I
This is
missed
what is
somewhere,
happening.
sir. I
Yeah,
couldn't even
I get
understand,
that.
sir.
I'm not. Do you understand this definition at least on paper? As in, given a map from L1 to L2, which are affine spaces, which can be written as V plus U1 and F of V plus U2. I can define a map from the underlying subspaces U1 to U2 as T of U is equal to F of U plus V minus F of V. And whatever I get, I want to check if it's a linear transformation, and if it is, then I'm happy. Okay, let's maybe take an example. There's one special case. Oh, I didn't give an important example, but okay, let's see. So let's take this x comma 1. What is x comma 1? Describe x comma 1.
A subspace.
This is an affine subspace. And this is actually y is equal to 1.
A straight line, which is
Now let me
over the value of
say,
x. It's a horizontal line.
Yes, sir.
yeah, it's a horizontal line. I want to take x comma 1 to, let's say, just one parameter shift. So let's just take this as x plus 1. So both of these are affine subspaces, right? I'll just take it to this itself. X comma 1, I take to x comma x plus 1. Is this an affine transformation? How would you go about checking if, okay, I used f for affine, let me use f for affine. Is f an affine transformation? If you want to check this, you write this as 0, 1 plus x0. So the underlying subspace for the domain is x comma 0. So what is x comma 0? This is just the x-axis. And what is this? This can be written as what is f of v. 0 comma 1 goes to 0 comma 1 itself in under this map. So this is 0 comma 1 plus xx. So this is your u prime or u2. Let me call this u1. This is u2. Now I define a map from u1 to u2. How do I define this map? This is defined as t of u is equal to, in this case, since it is vectors, I'll just say t of, what is u1? It is of the, any vector in u1 is of the form x comma 0. Now this is f of x comma 0 plus
Sir,
0, 1. Just
why
one
we
moment,
added
let me finish it. Yeah, go ahead now.
Sir, why we are adding 0 comma 1 and x comma x?
This is the affine space representation of that, no? X, any element x comma x plus 1 can be written as x comma x plus 0 comma 1. This is just writing that affine subspace as a vector plus a vector subspace. And what I've done is just use this definition. I want to write where does this v come from? V is a representative of the vector which you're using to translate the subspace. That is this v. So I'm doing f of u plus v. V is this. minus f of, okay, it has to be v, which is f of x comma 1 minus f of 0 comma 1. What is f of x comma 1? This is just x plus 1. F of 0 comma 1 is just 0 comma 1. So what is this? This is x comma 0 going to x comma x. So this map from u1 to u2 is x comma 0 goes to x comma x. Is this a linear map? Is this a linear transformation?
Yes.
Yes.
Yeah. So since this is a linear transformation, the map that we started out with, that is an affine transformation. So this is how you check. Okay, so what we were trying to do is checking whether this was a affine transformation. So in order to check that if that is an affine transformation, you have to take a representative vector and construct this transformation from the underlying transformation between the underlying vector subspaces, which is given by this f of u plus v minus f of v. That v being the vector which you're using to translate. And then you have to check whether that map is a linear transformation. So if T is a linear transformation, then F is an affine transformation. Spend some time with it, you will see, you will understand what's happening. But why is it defined this way is a deeper question, which I'll take up only at the end if there is time. So that's affine yeah, the important example of affine subspaces. So can you recall what, I mean, there is a specific example that I have in mind of a vector subspace, which is a prototype example of, yeah. So when we were discussing examples of vector subspaces, there was one special thing. Can you recall what that was?
Can you repeat the question?
Can you give me some examples of vector subspaces which are, let's say, not straightforward, like not lines in Rn or planes in Rn? There was one more special class of examples. Do you
Square
remember?
or square or XY, something like that.
No, x square will not be a linear structure, no? Like even if you're doing things like x square,
Forgot.
0 and all
No,
that.
I don't remember.
Like matrices or
Okay. Okay, not matrices. The next set of examples, very important set of examples, is the solutions to homogeneous system of equations. Is a vector subspace. Do you remember seeing this?
I'm trying
Does
to.
anybody remember?
Yes, sir.
Yeah. So one way to verify it is sum of two solutions will be a solution and scale of any solution will be a solution. In general, when you have, you know, n many independent variables, you'll get an n-dimensional subspace. You'll just keep one as t1, t2, tn, and then you'll see how you can express the dependent variables in terms of these independent variables. The number of independent variables will exactly be the dimension of the vector subspace. And yeah, this always contains 0, and this is a vector subspace. But what about the solutions to, okay, yeah, this is correct. What about solutions to ax tilde is equal to b, where b is not necessarily the 0 vector? Is this a vector subspace?
No.
No.
Sir,
No,
it
right?
should be,
Why?
no?
So if
Does
the
0 belong to this
equal to
space?
0, so obviously,
So if b tilde is not 0, then 0 tilde does not belong to the solution space. Let me call this guy as uh,
Sir, a
solution.
small, someone
Something.
is playing songs, sir.
Is anyone's mic on other than mine? All right. If there's any more disturbances, let me know. So 0 will not belong to U, right? If B tilde is not 0, then 0 is not a solution of Ax equal to B, because A times 0 will just be B, which is not 0. So therefore, U is not a vector subspace. U. And in general, Ax equal to B need not even have a solution, right? Ax equal to 0 always has the 0 solution, but Ax equal to B, it can be inconsistent. It maybe doesn't even have any solution. So what is the condition that ensures that B is actually, Ax equal to B actually has at least one solution? You can give me any one condition that which ensures that that works out.
If it is not inconsistent.
Well, yeah, that's just a reformulation.
Yeah.
That's not what I'm after.
A is invertible.
Well, if A is a square matrix, you can have A invertible will give you an unique solution.
Unique solution.
But in general, it is B is in column space of A. What does B is in column space of A? The columns of A span a set which contains B, which means that there exists an X which gives Ax equal to B. This is also a reformulation, but just in terms of more modified machinery that we are familiar with by now. So if B is not in column space of A, then U is just empty set. So that is not something we care about. We care about only the case if B is in column space, which means that this set U is not empty. Then U is an affine subspace.
Sir, I did not understand the meaning of column space. What's that column space? I mean,
Column space is the space spanned by the columns of a given vector. Again, week 4, week 5, something content
the
this is.
space spanned by the columns.
So,
Okay.
yeah, you have these columns, yeah, of a given matrix. If you're given a matrix, it has some columns. These are elements of an appropriate Rn. And then you take all possible linear combinations of them. What you get is the column space. And the dimension of that is actually called the rank of the matrix.
Okay.
Okay. So
So
if
for
B
check,
is in the column space, sorry.
sir, if we have to just check B is U is in a fine subspace, we just need to consider as B belongs to the column subspace. Will everything will be fine?
Yes. Just if your question is if U is an affine subspace, U being the solutions to Ax equal to B. If the solutions of Ax equal to B is what are the conditions which guarantee that this set is an affine subspace, then B is in column space of A guarantees it. And I have not told you why this is an affine subspace. I've just mentioned this fact. Now, suppose, now this is the proof of that. Suppose x naught tilde belongs to U, which means that is Ax naught tilde is B tilde. X naught tilde is in U means that x naught tilde is a solution to Ax tilde equal to B, which means that Ax naught tilde is equal to B. Now consider null space of A. This is what I use to denote null space of A. What is the null space of A?
All the vectors which are taking it to 0.
Yeah, Ax tilde is equal to 0.
What is
Right, so this is the null space.
why we are writing x tilde and what that means is?
So x tilde, it is just to differentiate between, like x generally is used to denote a real number. X tilde would be just a vector in Rn, in an appropriate Rn. So that n would be the number of columns of A. If that is confusing to you, then we can just, I don't want to change everything. Is that too confusing? I think this is standard notation by this point.
Just a real number, right?
It's a
Belong.
vector. So
Okay.
this A is, let's say, an m cross n matrix. Then where does this sit? This sits in Rn. So every element of this is an element in Rn. It's a vector in Rn. Right? So consider null space of A. Now my claim is that U is equal to x naught tilde. You take one particular solution and you add all possible elements of the null space of A. Then you get the entire U. So to see that this actually comprises of solutions of Ax equal to B, what do I need to do? I need to take an arbitrary element x naught tilde plus something in the null space. Right? Let me take y tilde in the null space. So for y tilde in the null space of A of x tilde plus y tilde. Now what is this? This is just Ax naught tilde plus Ay tilde. I'm just using the matrix multiplication. I'm just distributing it. What is Ax naught tilde by definition?
B.
B tilde. And what is Ay tilde by definition?
0.
0. But B tilde plus 0 tilde is just B tilde. So x naught tilde plus y tilde is also a solution. In other words, x naught tilde plus y tilde belongs to U. So what did I start out with? I started out with an arbitrary element of x naught tilde plus null space of A, and I showed that it is in U. So I have to show, strictly speaking, the other containment as well. But for now, I'll just say that you can verify easily. So if I take any particular solution of Ax tilde equal to B and add any element of the null space of A to that, that also is a solution to the given system of equations. So the important part to note is this, that the set of all solutions can be written as a particular solution plus some element of the null space, which is like taking a particular vector and adding a subspace. Null space is a subspace. So what is this? Vector plus vector subspace. This is an affine subspace. So that is why the solution space to Ax equal to B, non-homogeneous or not necessarily homogeneous system of equations, if it is not empty, then it is an affine subspace. All right. So this is all about affine spaces and affine transformations. And if there are doubts, I'll take it up at the end. All right. So because there's still more stuff to cover. Now we go back to vector spaces. This is why I feel that it is somewhat weirdly placed, that it comes in between and it is not used anywhere else and it just goes away. So now coming back to vector spaces. What we have seen so far is all these linear independence bases, transformations, matrices of transformations. Everywhere there was one thing that we were consistently doing, which is solving systems of linear equations. And these coefficients of the vectors, you're finding the coefficients of the vectors. So given any basis, how do you find the coefficients of a given vector in that basis? This was a common question that used to come up, especially in the context of finding the matrix of the transformation. So if using the notions that we will define in this session and the first session for the next week, we will see that finding those coefficients can be easy in certain bases. And that notion is the notion of inner product which is motivated by length and norm, length and angle in Rn. So this is what we will start out with, and we will eventually reach to a point where we construct a nice basis for any given vector space, which makes computations easier. So length and angle in Rn, I would guess most of you have some sort of understanding of this. So now let us start out with a very familiar point. Let's say this is 8, 6. I think that would be a nice thing to this vector. So using the thing that you know about R2, what is the length of 8, 6? The vector 8, 6. Did anyone say anything?
Underscore 8 square plus 6 square.
10.
Under root, sorry.
So this, and that is actually equal to 100. And this is actually 10. So how do you actually do it? This is 8 units. This is 6 units. And then you use Pythagoras theorem. In general, I'll use this notation. What is this equal to? Square root of x square plus y square. So this is the very familiar notion of length of a vector in R2. Now, there is also dot product in R2. For those of you who are familiar with dot product in R2, first I'll just start out with R2, but the same thing carries over for Rn. If I am given two vectors, let's say x1, y1 and x2, y2, what is their dot product?
X1, X2, comma Y1, Y2.
Plus, sir, not comma.
Oh, sorry.
Yes.
Yeah, not an issue.
Plus y1, y2, right? Yeah. Now this is a map from R2 cross R2 to R, right? You're given two vectors in R2 and the output is a real number. And what happens if you do xy dot xy? What is it that you get?
X square plus y square.
Yeah, x square plus y square. And what is that?
Length.
The length squared.
Length.
So length square. So this length and dot product are, of course, related to each other. And the next thing is about angle in R2. Even though I won't give a proof of why this is, if you have two vectors and the smaller angle between them is, let's say, theta, then let me call this u and v. How do I find theta? Does anyone recall the formula?
Cos inverse of
Cos theta.
Yeah, so cos theta
is
is
equal to mod of x and mod of y divided by
is
dot
this.
product.
I think it's the other way. No, it's
Dot product divided by.
Yes, sir. Dot product divided by the mod. Yeah, sorry.
Modulus.
yeah. This also you can actually give a proof of, at least in R2. But once you have the notion of a dot product, you can compute lengths and angles. You see that, and this dot product is just a map from R2 cross R2 to R. So this is what we will generalize when we talk about inner product on an arbitrary vector space. So all of this is for R2. I'll just say that similar notions for
Sir,
Rn. Yes.
what if mode and if u and v is only 1 1, then u mode is equal to
U is equal to what?
like the cos theta is equal to uv
U dot V, that this is the dot product between the two vectors divided by their norms. So this is also a real number. This is also a real number. Now I cannot define the angle between a vector and a zero vector. So the denominator also will never vanish. The numerator might.
if it is 2 and 2, u and v, then
U and V are vectors. So you have to give me two vectors in R2.
so we can say if 2 1 and 2 1, then we can do that, no?
Yes. You want this? In this
Yes.
specific example, what is the thing? So what is U dot V? This is 21 dot 21. And what is 21 dot 21? That is 2 dot 2, or this is not the dot, this is just 2 times 2 plus 1 times 1. Why the dot product is defined this way? You see, you add the first coordinates, you add the second coordinates. More generally, you add all the nth coordinates and add them all together. So this is 2 times 2 plus 1 times 1, which is just 5. What is norm of u? Which is the same as norm of v because you have taken u is equal to v. This is equal to square root of 4 plus 1. Right? Well, yeah. This is root 5. So cos theta is 5 by root 5. Or no, 5 by 5.
5 by 5.
This is 1. Cos theta is 1. When is cos theta equal to 1?
0.
Cos 0.
Theta is equal to 0. Now, did I have to do this, all of this to arrive at this result? Because what we are trying to do is find the angle, right? So what is the angle between a vector and itself? So if I just take the same angle, same vector, and maybe I just got in red to make it different. Okay. So what is the angle between these two vectors?
0.
It has to be 0, right? So this agrees with our intuition. The formula does agree with our intuition. It is, well, this is just one demonstration of that. This is not a proof, but this is a demonstration of that. On the other hand, if I have 1, 1, and let's say u is 1, 1, and v is 1 minus 1. What is u dot v?
0.
This itself is 0. So cos theta, I don't need to even compute what is norm of u, norm of v, and all that. This implies that cos theta is equal to 0. So what does this imply? Theta is
90.
90 degree or pi by 2. And this also you can quickly check by drawing the diagram out. This, and so 1, 1 is somewhere like this. Minus 1, 1 is somewhere like that. Yeah, it's exactly correct. Okay, this is fine because these both are at a 45 degree angle, no? So the angle between them is actually 90. This also you can verify either by actually checking, or you can use some graphing software and verify that this is actually at right angles to each other. Is that okay? The
Yes, sir.
same
Sir, that would be in the fourth
notions.
quadrant, na, sir. You missed it.
Oh, yeah, I did. Minus 1, 1. Okay. Let's do that.
Sir, what happened, sir?
What happened? With what?
Like I miss you made a mistake. I couldn't understand where was it?
No, no, the diagram that I made was actually minus 1, 1. I had earlier written it as 1 minus 1, so I just changed this V to minus 1. Both of them are
Okay, okay,
orthogonal.
okay, okay. I got it. Okay, yeah.
And then, yeah, okay. So given a vector in R2, how many vectors are orthogonal to it?
So in our infinite vectors should be, no?
Okay, let me ask that question. Given a vector in R2, how many vectors are orthogonal to it?
You mean vectors passing through the origin?
Well, yeah, vectors meaning always that. So are perpendicular. What is perpendicular? Perpendicular is angle between them is 90 degree. Yeah, and vectors always start from the origin.
The same thing is
So then
orthogonal.
then one.
Sir, two, I guess, sir.
There's one, there's two, there's infinitely many.
No, one.
So let's take a particular example. Suppose V is equal to 1, 0. What are all the vectors which are perpendicular to V? So
y-axis.
need U such that cos theta is 0. So perpendicular is equivalent to saying cos theta is 0, right? Theta is pi by 2, cos pi by 2 is 0. And this would mean that U dot V divided by norm mu norm V is 0. Now, the denominator doesn't matter as long as it's non-zero. So I need U dot V is equal to 0. So I'll write U as U1, U2 dot V is 1, 0. So the only condition that I require is U1 is equal to 0. Right? Because U1, U2 dot 1, 0 is U1 plus 0, which is just U1. So I just need U1, 0, U1 to be equal to 0. So any vector of the form 0, comma x, or let me write y in R, any vector from this is orthogonal to 1, comma 0. So there are infinitely many vectors.
Oh, okay.
So
I was thinking this as multiples of the same 0, 1 vector. That was
It is multiples of the same vector, yeah, but they are all different vectors, right?
correct. Correct.
so if a
0,
vector
1,
is
0 minus 1. Yeah, go ahead.
if the vector is 2 comma 0, then
If the vector that you start out with or the
the
vector that you need to be perpendicular.
starting
It
is
is
like
it'll be the same thing because you'll just get 2 U1 is equal to 0. Over here, you will get 2 U1 is equal to 0 instead of U1 is equal to 0. And 2 U1 is equal to 0 precisely when U1 is equal to 0. So the set is the same. And once again, they have the same perpendicular sets because they lie along the same line.
if
The
y.
angle between them is 0.
So every time a y change, if x is there and y is 0, then we can say u1 is to 0. If I say the vector is 1 comma 1, then it will be or not.
So okay, you want all the vectors which are perpendicular to 1, comma 1?
Correct.
Yeah, so this U should satisfy U dot V is equal to 0. So this is need, which is the same as saying U1 plus U2 is equal to 0. I've skipped a few steps over here, which is U1, U2 dot 1, 1 is 0. Now here you will need u1 plus u2 is equal to 0. And what is this? u1 plus u2 is equal to 0. This is the set of all vectors of the form x comma minus x. So this set contains vectors which are orthogonal to this. This is perpendicular to or orthogonal symbol. So in general, if I have a vector x naught, y naught, then the orthogonal complement of that, that's a word that is not introduced yet, would be something of the form y naught, x naught, and span of this. You can verify this. All right. So the methodology doesn't really change. 1, 0 I just took to have very easy computations. Even otherwise, it's the same. Now let's refine the question a little bit more and ask, given a vector in R2, how many vectors are perpendicular to it and have the same length as V? Would the answer change?
2, sir.
Yeah, this will be 2. And that again you can verify.
Sir,
It will be just 0, 1. Sorry.
is the answer 0, 1 and 0 minus 1?
Yes. But in general, if it is, say, if you start out with a vector 2, 0, then you will have to have 0, 2, 0, minus 2. And let's say in higher dimensions, this is a little bit slightly more advanced. Instead of saying given a vector in R2, if I say given a vector in R3, how many vectors are perpendicular to it and are of, say, unit length, then the answer would still be infinitely many, because in let's say 3 dimensions, if I'm given a fixed vector, let's say which lies along the z-axis, what would be all the vectors which are perpendicular to it? It would be this whole xy plane. All right. And in the xy plane, if you're asking for a fixed length, then you'll get a circle in the xy plane. I'm not sure if you're following this entirely, but you can see this, right? Like any vector on this circle is perpendicular to 0, 0, 1. So this is something specific to R2. The same result does not hold in higher dimensions, like number of vectors which are perpendicular and are of fixed length being a finite number is not something that is
So
true in higher
only for R2,
dimensions.
it's an exception case, right, sir?
Well, yeah, something like that. Because so it once again comes down to giving conditions, right? So if you are saying the perpendicularity condition gives you one restriction. So from R2, you remove. So I'm giving you a very vague argument, and this is not mathematically rigorous, but so you start out with R2, put one condition, which is vectors are perpendicular, then you get a line. That is what you saw over here, 0, y. And then you put another condition, then you're supposed to get finitely many points. Or sometimes, if it in this case, it's not a linear condition. Well, I'm not going to give you all that noise. But yeah, the more conditions you put, the cardinality decreases of the solution set. In this case, you're putting two conditions, so you're in some way expected to come to the least possible cases. In this case, it is 2 number of solutions. But in R3, even after you remove two conditions, you are still left with an infinite set. Is that at least vaguely okay?
Yes, sir.
Yeah. All right. Okay. Let's not dwell more on that. But yeah, whenever the question is given, you can, using the data in the question, you can determine what is the number anyway. This particular result, number of vectors perpendicular to a given vector and of given length being just 2 is specific to R2. That's correct. Okay, so for Rn, we saw that the notion of dot product gave rise to lengths and angles, and that the dot product is a function from R2 to R2. So this part of it may be a little bit abstract, This is just like the definition of a vector space. So what was the definition of a vector space? First, you studied Rn, the vector space Rn, and you knew the operations, and then we pick out what essential properties of Rn are there, and then we say that an abstract space satisfying these conditions is a vector space, right? So what was a vector space? A set, a plus, and a dot, and this plus is uh, v cross v to v. Addition of two vectors gives you a vector, and this dot was r cross v. You take a scalar and multiply it with a vector, and you get a vector. And you say that these operations satisfy certain axioms, 8 or 9 or whatever the number is. Now, observing the dot product and the way that it can be used to determine or define notions of length and angle, we have the following definition. Okay, so forget about this. That story I just told you, so that this also seems in the same vein of thought. An inner product on a vector space V is a function. Now there are different notations. This is one of the notations in this angled brackets. What does this function do? It takes as input two vectors and it outputs a real number. Whenever you have a doubt, you just think of the dot product. The dot product, what does it do? It takes two vectors in Rn, then you do v, u dot v and get a real number. Similarly, an inner product is a general function which operates on two vectors to give a real number, such that now this is not any function from v cross v to r is not an inner product. The properties that it needs to satisfy is that vv is greater than 0. Well, we say that it is greater than or equal to 0, and vv is 0 if and only if v is equal to 0. Let me write down the conditions first, and then I'll explain what has happened. This is for all VW anyway. All of the three conditions are all for all possible vectors. V1 plus V3 A V1 V3 V2. This linearity, this third property is sometimes split into two properties, one for addition, one for scalar multiplication. I've just put it in the same thing. So what does the first property say? If you take the inner product of a vector with itself, then you are supposed to get a non-negative number. So is this true in the case of dot product? What is the dot product of a vector with itself?
Its length.
It's the square of the length.
Yes.
Right. The square of the length is a non-negative function. And when is the length 0?
When the vector itself is 0.
Yeah, and no other case is allowed. So we just formulate this as this condition, that this function need not be the standard dot product, because this vector space V need not even be Rn, right? You have seen arbitrary vector spaces also. So whatever that vector space is, this inner product must function in such a way that the inner product of a vector with itself is always non-negative, and it is 0 only when the vector itself is 0. So inner product of 0 vector with itself is 0, and no other vector has the inner product of has the property that the inner product of that vector with itself is 0. So this is just non-negativity of, you can think of this as non-negativity of length of the vectors. if you want to connect it with the dot product. Now, in the dot product, also you see that the order in which you take the dot product is not does not matter, right? Like what is 1, 2, dot 3, 4? This would be 1, 3 plus 2, 4, which is 3 plus 8, which is 11, which is the same as 3, 4, 1, 2, 3, 4 dot 1. It doesn't really matter, right? Because it's x1, x2 plus y1, y2. Either way, it's x2, x1 plus y2, y1 also gives you the same thing. So the order in which you take the product of the vectors does not matter. So this is called symmetry. Symmetry meaning inner product of VW is the same as inner product of WV. And this is positive definiteness. Okay, I'll just write it. These names are not important to remember. I don't even know if the prof mentions these terms, but this is called bilinearity. And what this says is that you can take a linear combination of some vectors and then take the inner product with the third vector, or you take the inner product of the vectors and then take the linear combination with the same constants. It doesn't matter. So in some sense, it respects the vector space operations. So it is consistent with the vector space operation. You do the addition and then take the inner product, or you take the inner product and then do the addition. It gives you the same real number as the answer. And you can verify this property for the standard dot product also.
So is
So
this
this gives you
really used like I mean like I remember we did something similar for vector spaces also, where in like examples where 0 was not actually 0 but it could be something else.
yes.
Later
So
on we shifted to always vector spaces with 0 only.
correct. So in this course, most of the examples that you will deal with will be Rn vector spaces of subspaces of Rn and things like that, where this abstract definition may seem unnecessary, but there are places where different inner products or different vector spaces structure have their merit. Off the top of my head, I cannot remember exactly an explicit example, but you will later on definitely see. At least in the case of norm, I can remember something that I will tell you when I'm discussing norm. But yeah, this might seem hopelessly abstract at this point, but it is useful. Like the non-standard structures are also model spaces for some notions.
Okay.
Yeah, but for the purpose of this course, you will see that most of the time you will be dealing with the standard inner product on Rn itself.
These are only
But
applied to the
this,
vector.
could you repeat that, please?
Sir, V cross V, it is a V cross V product or V dot V product?
No. V cross V is just the Cartesian product of V with itself. It's the set of vectors V comma W. It is just two vectors. It is a set of two vectors. So what it means is just that this function, it operates. So what is a function? It takes something from the domain and gives you something in the codomain. What is the domain? Domain consists of pairs of vectors, ordered pairs of vectors. Well, apparently in this case, the order doesn't matter because of symmetry, but still, you will take an ordered pair of vectors and spit out a real number. The codomain is a real number. So that's what this V cross V means. It just means it is pairs of vectors. All right. So if you want non-standard examples, you can take things like non-standard examples on Rn itself. You can take something like 3, 4, 1, 1, x2, y1, x2, y2. So this would be what? X1, y1, 3x2, plus y2 x2 plus 4y2. You might not understand what I'm doing right now. X2. Just give it a bit of time. Give me a bit of time. X1 y2 plus x2 y1 plus 4y1 y2. So take this as your inner product. So I define inner product of x1 y1 and x2 y2 as this quantity 3x1 x2 plus x1 y2 plus x2 y1 plus 4y1 y2. Now the ordinary inner product was just x1 x2 plus y1 y2, but here we have some more terms. You can verify at your convenience that all these properties are satisfied. Now use symmetry is obvious, right? If I change x1 to x2 and y1 to y2, the thing doesn't really change. Do you see that at least?
Yes.
Yeah,
So
but
the above,
non-negativity, sorry.
so the above part where we multiplied 3, 1, 1, 4.
Yeah.
That is
So
like a,
this this is okay. This is a slightly, as in this is a concept that is not covered, but there is a, just like there is a matrix of a linear transformation, there is a matrix of an inner product, and that matrix needs to be a symmetric matrix. And as long as it's a symmetric matrix, a positive definite symmetric matrix, all of these terms you might not even come across in the course. So I'm not going to tell that. Then you will get a representation of this form. I just used it to manufacture an example of something which is non-standard. Uh, but to prove that, for example, this is always positive, might not be that easy, right? How will you prove that this is always positive? Or okay, in this case, this is not something that you need to prove. So if I have xy, that needs to be positive. And what is xy? It would be 3x square plus 2xy plus 4y square. Now, is this always positive? You can do some manipulation and check that this is actually always positive. It is not immediately obvious. You'll have to do some completing the square and then maybe check what comes of that. You need that this is greater than or equal to 0 for it to be an inner product, right? So we are trying to show that this is an inner product. I'm just telling you what are the conditions that you need to check. That you have to check that this is greater than or equal to 0, and it is 0 only when x is equal to y is equal to 0. That is your first condition of positive definiteness. Symmetry is obvious. And then there is this bilinearity. Bilinearity also you can check. Bilinearity is easy. Maybe here the only thing to check carefully is the positive
sir,
definiteness part.
Yeah, it is
Yeah.
coming to greater than 0 because x product of xy will always be less than the other two sums. And those are
Yeah, that is what you have to somehow prove.
yeah.
So how would you prove that? So you can write this as maybe 2y plus x by 2 something like this square, which is 4y square plus 2xy. No, that would just be xy.
So
Yeah, I'll have to do
we can
something
assume
like
one,
this.
that if x is greater than y, we can just take that. That means y square is greater,
Just
and
one
then
moment,
y will
just
always
one
be less
moment.
than one of them, right?
No, this is not even this. How do I complete the square? I've completely forgotten.
No, it is better to do it as an argument, right? Like, see, if we take, one of them is greater.
I think it is this only. No, just one moment, one
Yeah,
moment. Yeah, maybe your thing is easier, but this is also fine, no?
correct.
sir, I want to ask one
Yes.
thing.
Yeah.
When we do the inner product of xy, comma xy, then how
Mhm.
we get compute it as 3x square plus 2xy. 2xy is okay, x square is okay, y square is okay, but 3 and 4.
3x square, you
Equate
have the
it into the
3x1, x2, no?
previous equation. No?
So you put x1 is equal to x2 is equal to x over here, and y1 is equal to y2 is equal to y2. I'm using this formula. No? So that's how I get 3xx, which is 3x square. And then I get an xy plus xy, which is 2xy, and 4yy, which is 4y square.
Okay, that was for the above one.
Yeah, but this is, I'm dealing with this example, right? I want to show that this definition also gives me an inner product. And the way I'm going to do it is verify each of the conditions. So the first condition was this. So I want the inner product of any vector with itself to be non-negative. In this case, it will be like you can complete the square and do this. Maybe your method is faster or easier, but this is one way to do it. Let's just complete this, and then you can tell me what you did. This would just be plus 11x squared by 4. So these are sums of positive numbers, so they have to be positive, at least non-negative. And if it is equal to 0, then both these terms, this one and this one, have to be 0, which is x is equal to 0, and then consequently y will also be equal to 0. So positive definiteness is also verified. 2 and 3 are easy. Let me say trivial, but you have to check it properly. Okay, so this actually gives you an inner product. What was your method?
No, I was just saying that we can take that, like one of them is the greater value, like say y.
Okay.
If we assume y is greater, then we can say that we can set x is also equal to y. So its maximum value 2xy can take is 2y squared, which is less than 4y squared. Or vice versa, you can take it on the x side. So if you say x is greater than y, then it will be 2x squared, which is still less than 3x squared. So that we can.
Okay. So you are doing something like 2y into.
I mean, I'm just
2y
making an assumption that
minus
let's assume
x
x is greater than y.
minus.
It's more of an argument, not a mathematical.
Yeah. Okay. Fine. Yeah, whichever way you can, as long as it's mathematically sound, it's fine. And yeah, to me, this is more natural because we are dealing with quadratic forms, right? So this I can just complete the square and the residue as long as it's positive. If it was something like this, then there would be more work required. So just give me a moment. I'll be back in a couple of minutes. Yeah, okay. Sorry about that. Let's get back. Right. Where were we? Inner product. So as soon as you have an inner product, you can define length and angle. So length of a vector. So what would you guess is the length of a vector in a vector space with a given. So if I have a vector space with a given inner product, what would be the length of a vector v? Let me use this thing.
Sum of squares of all the components, square root.
But this might not be an Rn, no? So here we are taking the more abstract approach. So in the case of dot product, what was it? In the case of dot
V
product of,
dot
let's
V.
say, R2, so we had xy to be equal to x square plus y square, square root of that. But what was x square plus y square? This was xy dot xy. So this dot is what we are generalizing to an inner product. So what we will use is the square of v dot, or inner product of v with v. Okay, so this in an arbitrary inner product space, this is called an inner product space. A vector space with an inner product is called an inner product space. Okay, so the square root of the inner product of a vector with itself is the length of the vector. And this makes sense. Why does this make sense, or what is the possible way in which it would not make sense? I'm doing an operation while defining which is not always well defined. What is that? I'm taking a square root, right? When can you do a square root?
A non-negative number.
Yeah, you can take only square roots of non-negative numbers. And are we guaranteed that the thing under the square root is a non-negative number?
Yes, sir.
Why is that?
Sir, when we take dot products, the components are multiplied with each other. If one of them is negative, then
That
negative
is
into
the
negative.
that is dot product. But what for general inner product?
By definition, we say that it is.
Yeah. So definition 1 gives you that this positive definiteness, what I've called positive definiteness, it says that the inner product of any vector with itself is always a non-negative number. So I can take the square root of a non-negative number, and that is all. I'm good. And also, length of a vector is 0 if and only if what?
The vector
Can you
itself is
complete
0.
this? Yeah. Why is this? That is also because of property 1 itself, where it says that inner product of a vector with itself is always non-negative, and it is 0 only when the vector itself is 0. So length of a vector is 0 is equivalent to saying the vector is 0. Okay, this is for an abstract. Okay. All right, there was a lot of echo there. Okay. Yeah. This is for an abstract vector space with an abstract inner product. Whenever you have any doubt, you can quickly refer back to the dot product, but you should know that this is valid in an abstract inner product space as well. So similarly, we can formulate the notion of angle of a vector, angle between vectors. So let me call it angle theta between vectors v and w. So what would this be? Let's write it in terms of cos itself. Cos theta would be what?
V dot W over.
In
No,
angle
that was
bracket
v dot
VW.
w. Yeah, so this would be the inner product of vw.
No, no.
Again, norm of v, norm of w is using this notion, not necessarily the usual. There's no length of the vector as we know it, square of the components, sum them and take the square root. It's not that. It's just you could write it as ww and square root of that.
But can we, like, using your other definition, like you had given that example of another inner product, can we say that
Yes.
will also be this cos theta, which is the same as we talk about? Cos theta.
No. Cos
This
theta,
which
this notion of angle, we are defining with respect to this given inner product. So if your question is, can we have different notions of angles and lengths? Yes, that is correct. As in, what may be orthogonal in the usual sense may not be orthogonal over here.
Oh,
Okay, so let me see if I can give a quick example using this inner product. If I do 1 minus 1, three plus. I don't. But you can check that not always will you have the same orthogonal vectors.
oh,
Here I'll have to see the nullity of this. It's fine. For now, yeah. Lengths. Let's see lengths. What is the length of 1, 0 in this inner product? That we can always do.
Three.
This should be 3, right? I mean, square root of 3, but yeah. If I substitute y is equal to 0 and x is equal to 1 in this, I'll get 3, which is the square of the length. So root 3. But in the usual inner product, your length of this would be just 1. This is a standard basis vector. So by using different inner products, you are sort of changing the notion of length and angle of a vector space. And this might be useful in certain cases where when you represent data using points, there might be something which is the notion of length of that might not agree with your usual thing. I cannot tell you more than that right now. But yeah, probably in the future courses you will see where non-conventional notions of lengths and angles give you a better meaning for the data. In any case, okay. Even over here, I can use those vectors only. If I use 1, 0, y1 would be 0, so I'll get 3x2 plus y2. So I'll just need 3x2 plus y2 to be 0. So I can take 1 and minus 3. Yeah, this should work. So this is orthogonal to this. You can quickly verify that this is orthogonal to that. And that's not orthogonal in the usual sense, right? The angle would be something else. It would be 1 by root 10, cos inverse of 1 by root 10, something like that. But in this case, it's orthogonal. All right. So that's all about angle and length. Angle and length, what you need to know is it's defined with respect to a given inner product. For most examples, for most questions in the course, you'll probably be given the standard inner product on Rn, and you'll be dealing with subspaces of Rn, just as someone was remarking earlier that we studied this notion of abstract vector spaces, but then ended up using Rn anyway. This might happen in this case also, but remember that this is relevant, that the more general notion is also relevant in certain scenarios that which you might see sometime in the future, not necessarily in this course. So that's the notion of length and angle given an inner product. So when you are given an inner product space, now you have like 3 operations: a plus, which takes in 2 vectors and adds them and gives you another vector. Then you have a dot, which is the scaling of a vector. You are given a real number and a vector, then you can scale the vector and get another vector. And now you have another operation, which takes 2 vectors and outputs a real number. Addition, scalar multiplication, and now an inner product.
Are we still dealing with the vector space? I mean, I mean, B plus dot and that inner product is still vector
That
space
is the
or?
most general scenario.
Mhm.
But for most examples and problems that you will solve, you will be using Rn and standard dot product only.
Okay.
But all of these things that we have discussed are valid for the most general notion of vector spaces.
So can we say that the angle is mostly important only if the angle is like 90 degrees or zero? Other than that, nothing really matters.
Yes. I mean, I wouldn't say that, but orthogonality is an important concept and it will be the primary focus of the content of next week, as you will see.
Okay.
Okay. Those are the two extremes. No, like a vector lies along a vector and vector is orthogonal to another vector. So if a vector is orthogonal to another vector, then this is in some sense farthest from being dependent on this vector, because let's say you're looking at the projection of this vector onto this vector. Projection again will make sense only in the next week, but this will have zero projection and all that. So orthogonality implies linear independence. This is something we will see next week, and that is why orthogonality is interesting, at least in the concept of in the context of linear independence. All that we'll see next week. That's a very nice observation that orthogonality is what will lead to interesting things, and that is true, and we will see. But that does not mean the general other angles are not important. The lesser the angle, the more the dependence there is. That it can be quantified that way too.
Mm.
But okay, back to angle, and now we'll define what norm on a vector space is. Once again, now there will be some abstract formulations, and you will probably be using only length of vectors in Rn. But I'll give the general notion of a norm as well. So norm is like length. Okay. So on a vector space V with a plus with a dot, now don't assume that there is an inner product. Just assume that there is a vector space V with a plus and a dot. So it's just a vector space. Then a function from V to real numbers is said to be a norm, a function such that the following three conditions hold: that the norm of every vector, why do we use x, we use norm of every vector is non-negative, and norm of a vector is zero if and only if v is zero. This is similar to the first property of inner product, but there you had two inputs. Here you just have one input and you're just looking at the norm of that vector. The next one is something like a linearity property. What would you expect this to be? The norm of the scale of the vector is equal to,
C square.
no, this would be mod C actually, for all V in V and C in R. So this needs to be compared with length, right? So if you have a vector, let's take the simplest vector 1, 0, that has length 1. What is the length of 2, 0?
2.
That is 2, right? So that is twice. So 2 times 1, 0, the length of that is 2 times the length of 1, 0. So there's no squaring happening over there. And similarly, if I have say minus 2, 0, that is also length 2 itself. So that is why this modulus comes. So you cannot have the length to be negative. and that is in the more abstract case that we are dealing with also, that we need every vector to have non-negative length. That's why this mod comes out. So scaling a vector scales its length also, but the mod is there just to make sure that it stays positive. And then we have the final thing, which is called the triangle inequality. This needs to happen for all vectors. You can verify that this happens for the standard notion of length. But yeah, once again, this is, instead of saying this is the notion of length in Rn, we say that for any vector space, you can define a notion of length. And as long as that notion satisfies these three properties, then we can develop reasonable theory. All right, so this is a norm. A norm is a function from V to R. Now you are just taking one vector as an input and outputting a real number, a positive real number actually, a non-negative real number. It is 0 when the vector is 0. And this is a norm uh, on a vector space.
Sir,
Now
over
I'll
here,
just,
when you say norm of V, we are basically dealing with the standard dot product, no?
no, there's no dot product. So I'm just starting out with an arbitrary vector space and then saying that any function which takes a vector as an input and gives out a real number as output, satisfying these three conditions, is called a norm.
Sir, but what would be the definition of norm of V over here?
Okay, let's take an example. So just like over here, I said that any inner product is a function with these properties, and then we gave a non-trivial example, right? So as long as the inner product satisfies these three conditions, then we call it an inner product. As long as the function satisfies these three conditions, we call it an inner product. Similarly, as long as the function satisfies these three conditions, we call it a norm. It could be any function which satisfies these properties. That's why it's the definition. Now let's take R3. And on R3, I'll define this norm as, I'll define a function and I'll prove that it's a norm, that this, what is the usual definition of a norm? That would be square root of x square plus y square plus z square. Instead, I'll take mod x plus mod y plus mod z. So this is how I'm going to define this function. Is this function going to satisfy the three conditions? Is
Yeah.
it non-negative?
Yes, non-negative.
It's non-negative because it's a sum of three non-negative numbers, and it will be 0 only when all this is equal to this is equal to this is equal to 0, which means that x is equal to y is equal to z is equal to 0, and you are dealing with 0 vector. So first condition is okay. Now second condition, if I take c times a vector, I'll get a c over here, a c over here, a c over here, and that mod comes out. Mod c you can take common, and second condition can be verified. Is that okay?
Oh, yes, sir.
Yes.
And third condition requires a little bit more work. You can square those two things and compare the two terms. Instead of R3, you can do the same thing on any Rn. So let me take the specific case of R2. The proof for any Rn is not much different. So in this case, what does xy go to? Xy goes to mod x plus mod y. This is my new norm, right? Now, to verify, in order to verify three, once again, 1 and 2 are easy to verify using the same thing. What do I need to verify? I need to verify that modulus of x1, y1 plus, sorry, norm of x1, y1 plus x2, y2. This is less than or equal to x1, y1 plus norm of x2, y2. But okay, let's compare the two sides. On the left hand side, I have norm of x1 plus x2 y1 plus y2, and that is equal to modulus of x1 plus x2 plus modulus of y1 plus y2. This is by definition because x1 plus x2 is the first component, y1 plus y2 is the second component, and I have to take the modulus of the first component plus the modulus of the second component. On this side, I have modulus of x1 plus modulus of y1 plus modulus of x2 plus modulus of y2, right? Are you with me?
Yes, sir.
Yeah. So can you see that this is less than or equal to this? This is by simple triangle inequality for this itself. So this is actually less than or equal to modulus x1 plus modulus x2.
Yes, sir.
Yes.
And this is less than or equal to modulus y1 plus modulus y2. This is triangle inequality for R. Now, and that shows that this is actually a norm. The same thing you can do for R3 as well. In R2, there is an added advantage that I can show you something. That what does this norm actually capture? So if I have a point xy, let's take some specific coordinates. Let's take say 4, 3. Now the length of this 4, 3 in the usual sense, what is the length? I'll just call it length of 4, 3 standard. What is the standard length of 4, 3?
5.
Distance from the origin.
Yeah, distance from the origin, which is 5. Right? Where Pythagoras theorem gives you 16 plus
Yes.
9 under square root will be 5. But what does that actually capture? That actually captures this distance, the distance from the origin. But what is this saying? The norm of 4, 3 in the new metric, I'm not going to write standard for this, but in this metric, what is this? What is the length of 4, 3 in
4
this?
plus 3, 7.
So it is actually 4 plus 3, which is 7.
Manhattan
And
distance.
what is this actually capturing? It is like you're going from here along the x-axis, you're going to 4, 0, and then you're going 3 units above, or the other way. Sorry. Yeah, no, this is correct. 4, 0, and then I'm going. So I travel 4 distance over here, 3 distance over here. So this is why it's also called the taxi cab metric, because it does not say that the distance. It is like it's some sort of relation between displacement and distance. Even though this is the shortest path, or actually the length, if you were in a taxi cab which can only travel in the lattice, or which has only roads along the integer lines, then it would take a minimum of 7 units to get to that point. That is what it is saying. Did you understand that remark?
Yes.
So if there are no roads, you cannot take this path, right? You cannot travel. You cannot go 5 kilometers and reach that point. If there are roads only along the integer coordinates, then the distance that you will travel to reach the point 4, 3 is actually 7. So this is called as taxi cab metric, or Manhattan distance. I'm not familiar with. Maybe that's another thing, another name for the same thing. So yeah, that's why, even though you have a standard metric, maybe there are scenarios where other metrics are useful. The distance, the way you measure distance, has to also be feasible, right? As per the definition of the problem or the problem setting, you might need another notion of distance. So this is the most general notion of distance, and you see that this is a non-trivial example. As long as these 3 conditions are satisfied for a function defined from the vector space to R, then it is called a norm. Is that okay?
Yes.
Yes, sir.
So the last thing to talk about is inner product induces a norm. I'll just mention this. I'll just state this. So if is an inner product, then V goes to the length of the vector. So you can define the length of the vector in terms of a given inner product. The length actually is a norm function. This is what it says. This is a norm. So you use, typically we use norm and length interchangeably. Both mean the same thing. If it is within Rn, we usually consider, if nothing else is specified, then it is the standard inner product or the standard dot product and the notions associated with it that you have to use. But if a specific inner product is given to you, then you'll have to work with that inner product. And that ends all the topics that needed to be covered. There is a variety of topics over here, as in, like we started out with affine subspaces, affine transformations, lengths, angles, inner products, norms. It might be a bit much, but just go back and review it once again, and yeah, it'll come with time. And this is where we will stop the session. If you don't have any doubts, feel free to leave. If you have doubts, yeah, just ask away.